So the component's got to run somewhere, and where will the components run? An ESB. But the ESB has to have certain characteristics, right? So we'll talk about that as well. So again, event-driven. Event-driven means a message, something triggers a component, it does some work, generates a message, and it's fire and forget. It sends the message off. There's a route. Someone has said, hey, you got to go somewhere. It goes to the other point. As soon as it comes in, the event is triggered. That's what you mean by event-driven, right? The message goes in, second service processes it. That's how it works. So, what this essentially implies is that when you have two services or multiple services, the document is flowing between them. The document is like the interface. When the document or the message goes from one service to the other second service that is receiving the document reads the document, has to understand it. If it doesn't understand it, then it just throws an error right there. This is what Jason meant by the client. The state is in the client, right? There's no central state management. The state of the system is carried in the documents or messages that flow across the distributed services. So think of, services distributed across a network. For a moment, you don't have to worry exactly about how the services are actually running, right? Services are distributed across the network. Messages are flowing between the services, and the message itself carries the state. The state of the system or the message is augmented as it moves across multiple services to solve a problem. There's no central database in which you keep maintaining the state. That's a very different concept from web service centric, or even take integration scenarios. You take a classical integration product like Microsoft BizTalk, or IBM ESB, or TIBCO, or Oracle, anyone. Essentially, they've got a BPM engine at the bottom, and although you see these visual flows, right, that A is going to be in pulling out database, pulling data from a database, transforming it, putting it into a file, sending an email. What's really happening under the covers is you pull it from the database and go to the central engine. Central engine stores the information away, saying, okay, this step is over, and sends it to the next guy. Then you come back to the central engine. So all the information of the state is managed at the central engine. So if the power goes off and it comes back up again, the central engine should have stored the state somewhere. But if you don't store it, then you're toast. Or suppose you've done 10 transactions, right? After the 5th transaction, you checkpointed the state, you stored it. At the 7th transaction, 8th transaction, 9th transaction, the power went off. So when you go back and read the information again, you only got the information tells you 5 transactions have been done. The next 3 transactions have been lost. That's what happens with central state management. But that's what people don't tell you when they're selling the product to you. With the REST-based approach, that doesn't happen because the information is flowing between the services themselves. If the power goes off, the message is still there. It's a persistent message, right? The message is still there. When the power comes on, it just starts off where it left off. This is a very critical point. Here's an example. Take a real example here, right? So you take a simple document. I'm looking for the client application sends employee ID and needs the employee details in the response. The way this would work is you send a message off to this, you route paste in the URI, get the employee details. So what the incoming message is this, saying I want the details of employee number 1985, and the employee, this particular service will actually go and access some database, the employee database, get the information, but where will it store the information? Not in some central engine. It will just put the information into the message itself and send the message off to the next service. So it's fire and forget. I've done my work. The service says, this is the difficult part. We're used to this concept of request reply. We're used to the concept of programming from day one. We're taught as programmers, a function call, it's finished. So I go somewhere and I come back. Then I get to the next step. I go somewhere, I come back. So we use the term request. The client application sends employee ID and needs details and response. Request, response. You think it's request, response. But what's really happening here is you're sending a message to a service saying, hey, give me this detail. The service somehow gets the detail, puts it in a message and says, okay, take it. Do whatever you want. So from this point to this point, yes, it's synchronous. But basically, once the data comes in, you get the data and you push it out. From here, it can go anywhere. This is what you mean by hyperlink. It doesn't necessarily have to be HTTP hyperlink. It is a term that Jason was using at an abstract level. Here, the message flow is what is triggering everything. So think of it as essentially messaging middleware with cool tools that can be used to implement REST-based SOA. Right? So all state information is carried in the document. No state information is stored in any central server. The documents are dynamically augmented with the state information as they are processed by services across the ESP. The services themselves don't have to be running in a single location. The services can be running in different locations on a network. You have to find some way. This is what Jason meant by saying that resource metadata is managed by the ESP. The ESP knows which service is running where. A database service is running on this machine in Singapore. A file service is running in Kuala Lumpur. Right? That's all it knows. It doesn't know what actual data is being transferred between them, and it doesn't store anything by itself. Right? So this information, this makes it very interesting because information is never lost due to system shutdown or restart. On restart, the processing picks up where it left off with no loss of state, since all the state is stored in persistent documents. When data is picked up in Singapore, it's just transferred straight off to Malaysia via a message. If the power goes off, well, the act doesn't come back. So under the covers, nothing is lost. This is a very important concept. So key characters, the messages are the sources of information. They're really the documents, the messages that are flowing between the components, right? Now, messages contain documents. There's no RPC or equivalent. For instance, RPC, as we said, RPC is popular because programmers can understand it easily, right? So documents and messages, just think in really simple terms. I'm going to have a lot of services, messages are going to flow between them. That achieves the goals of REST-based SOA. I know it sounds overly simplistic, but that's literally what it is. It's really not complex. This is the whole point, right? Content routing. As messages are flowing from one service to the other, how does the second service route them? It could route them based on the content of the message. Right? So you don't know at compile time where the message is going to go at runtime. This is a very powerful concept. Because you as the service developer can decide, okay, if the message is like this, I'm going to create another service, I'm going to send it somewhere. And I'll put a service there to make sure it gets done. So it gives you a lot more power. You don't have to go and think of designing some crazy WSDLs and doing all sorts of tight coupling and then in one central edge and buy 25 CPUs to run it. You see, that way, the problem with that approach, the traditional approach is, if there's one small error, then the whole thing stops. With this REST-based approach, everything is running. If one client messes up, fine. It will throw an exception and get handled. The rest of the system keeps carrying on. That's another very interesting point. Partially, the system could be down. A partial system down doesn't bring the whole system down. Very interesting point. When you're working on REST-based SOA, how you design the messages that are flowing between the services are important.
It wasn't doing that for me.
It's kind of wacko. I think it's just me. It must be my hyper voice or something.
I think it's the time.
It could be the time. So document characteristics, right? The word interface, what it means, but the document is the interface, means when one document is flowing from one service to another service, obviously the second service has to understand its format, right? I mean, if the second service is coming in, you send it a document which it doesn't understand, it's going to throw an exception. So it's a fancy way of saying the document is the interface. Right? You have to, as the developer is developing different services, he has to make sure that the document formats are going to be understandable. It's important to all of the information that is required for one service to understand a document should be in the document itself, so self-describing, right? XML is used a lot, but not necessary. You could just have text files flowing around between services. It's up to you. You decide. The developer decides the format of the documents that flow between the services. So it gives you a lot more power as a developer, right? So it's not dependent on any particular stack of software saying, the Oracle guy said it's got to be like this, I got to put my web services implementation this way, etc., etc., etc. Nothing like that, right? The so-called contract doesn't have to be defined explicitly. As long as you can make sure that, you can have a long document, but one particular service might only read the first 3 lines. And that's fine, right? So that's really what it means. So there's no explicit protocol about how you're going to receive things. You don't waste too much time. It gives you a lot of flexibility. But it is a different way of thinking through things. It's fully asynchronous in the sense that when you have a flow, we still talk in terms of I'm making a request. I want something done. The request, the so-called request, goes through multiple services and comes back. But these steps are all asynchronous. You see the point? It's as if you're doing request reply by saying, okay, get this done, goes through 4 or 5 steps, and gets back to you. There's no fixed time. It's really a fire and forget type of operation. This takes a little bit of getting used to, but this is how at least the Fiorano tool is designed, and you get used to it. So here's the request document saying, I want the bank account for 1985, and this is the response. But this doesn't mean that at the programming level, it doesn't mean I make a request like a programming language and wait and somehow magically it comes back. No. What it means in real terms is, like the previous flow I showed you, this gets put into a message and gets sent to a service. That service does some processing, gets the data and sends it back to another service that might store it in some database and just send you an email about it or just do something, right? Or show it in your UI. So the whole cycle is asynchronous and it has many advantages for scalability. Logical routing, everything is a resource that we talked about. When you have different software tools, right? If you have different services, each service might have multiple input ports and output ports. Everything can be addressed via a URI, right? This is something that it really depends on the software tool itself. In the Fiorano case, we have software tools when you allow you to simply draw lines between the components. And a line drawn automatically signifies message flow at runtime. Sort of like the link between 2 services, the so-called hyperlink, right? So, and the Coast Guard had its own URI policies that they used. So ESB routes, filters, and enforces the policy via the URI. So this is sort of like what the message will look like, but it's just a generic diagram, right? So here's an example from an actual Coast Guard flow. So if you really look, you see the steps, look at the various steps, right? The first step, you make a sort of request. The web client says, okay, I want something. And it goes into the request queue. See, it's not as if it's going to one program and that's doing a lot of work and coming back. All the lines represent asynchronous transitions, right? The second step goes to, the message gets transformed for a number of reasons, right? And then it goes into a different request queue, the message gets validated, and then you want to communicate with a different subsystem. Let's say you want to talk to a particular web service to get the answer, right? And there are ways in which, depending on the ESB, you talk to that. You put it in a different queue, the job manager picks it up asynchronously, goes to the parts service and validates it. You can just do multiple hops. Now the benefit of this approach is, what if somebody came up with a better parts service, right? You could literally pull this out and put the other one in. So asynchronicity in your operations gives you tremendous amount of flexibility, right? This is something that with a little bit of practice you'll get. The most confusing thing about REST-based SOA and the asynchronous approach is that everyone's used to this request reply way of programming. So RPC started programming. It takes a long time to get out of that. or at least you need a little bit of experience. And it's not that difficult. After a couple of hours of using a software tool like our tool, then it becomes quite obvious. We've been doing this for years, by the way. It's just that it was the obvious thing to us, but apparently it's not obvious. So document managed state, standard interface, asynchronous messaging. So this can be thought of. Suppose you didn't use any tool like a visual tool like Fiorano. You could just use JMS. You could literally just do your own JMS programming and achieve the same results, right? So that should be so there's no build time mapping to particular resources. Senders and listeners can talk any message types and can send them anywhere routable. Whereas in contrast, if you look at the WSDL approach, right? It's all tightly bound. Resources are loosely coupled to message contents. When you come here, the message validation, you can send it anywhere you want. Message routing services can, for instance, look at step 14. Depending on the content of the message, you can send it to a multiple set of listeners, right? It's not determined at compile time, whereas in the web services approach it would be, right? Dynamic typing. Any particular service can handle it can handle integers, strings, characters, different data structures, all at runtime, right? Again, a lot depends on how you design it. So why messaging is critical? Asynchronous. Everything should be asynchronous. Message is retained at the last stop. If power goes down, you pick up where you left off. This has a tremendous number of implications for scalability and availability, which are very critical in all your mission critical applications, right? So the runtime environment has to be rich in terms of exception handling. At runtime, you get a message which you don't understand, you should be able to throw an exception and give it to an exception flow, right? Handle it, which is something again that depending on the implementation. Certainly the Fiorano ESB does it, and there'll be other ESBs that do it as well. Late binding. Scaling up. Right, this is really a good example. Depending on the content of an incoming message, you can route it to different services at runtime, right? And they can all be operating in parallel. It's all done asynchronously. Messages coming in, you route it here, write it there, and you can add more even while the system is running because all the steps are asynchronous. What asynchronous means is that at runtime, while everything is running, I can actually literally create another service and add a line saying that, when any data comes to this port, it's given to both of them. Add a fourth line. So you can modify the system at runtime, add steps to your business processes without stopping the existing business process. This is very critical. You can in fact stop one of the processes without stopping the rest of them, because everything is operating asynchronously. So for example, if I stop this get employee details process, the other two processes will keep operating. If any message comes in here, it is simply queued up. I could actually stop it, replace it with the updated process without stopping the whole application, restart the particular service, and the queued up messages will get processed by the new version. You can do all that in practice, whereas with the traditional approach, you're going to have to stop it and recompile the whole thing, redo the whole thing. It takes a tremendous amount of time. Right? Okay. So now I'm going to just show you. Can you switch to the next presentation?
Yeah.
Yeah, just switch. How do you switch?
Oh, yeah, it's just
I'm just not used to it. Oh, there it is.
Fine.
Yeah. So now we're just going to go over some of the projects that the Coast Guard actually did, and that's just informational. So they had 50 different businesses: law enforcement, logistics, maritime, domain awareness, financial, all kinds of services and different applications have been implemented. They use Java, they use .NET, Oracle Forms, Visual Basic. So this is one of the projects. They had 11 prototype services developed in just 2 days. See, once you develop a first set of services and get the hang of it, snapping things together and creating the flows is very quick. Because you don't have to worry about things like central state management and any other jazz. It's all done for you. only one downtime because of hardware failure. Aviation logistics management systems, again 2 production services in a month, 18 months for operations. Vessel positioning services, this is an interesting one. There's some visual diagrams here. Vessel position services means that essentially there are 6,000 vessels that are around the United States at any time. They wanted to get the information. Each vessel every 3 seconds gives out this sort of radio message, and that's picked up at the shore and is pumped into the ESP, and then they wanted to get all the right information about each vessel, what it's doing, plot it on a graph, get it with Google Earth so you can show the Navy commanders or any of the government people exactly what's going on. Right? So here's the result. It's all dynamic. You could actually zoom in, and then for each vessel in real time you will know where it's headed, what its mission was it interdicting any drugs or whatever. All sorts of extremely interesting information. It's all live. It's like a global live system running, and they were able to do this just within 3 months, get the whole thing up and running. Pipelines, rigs, Deepwater Horizon. When the Deepwater Horizon disaster occurred, the oil well, it took in 4 days they actually designed, built, and made live an application that actually showed exactly how. In fact, that was the previous one. The previous diagram was the Deepwater Horizon stuff. This is the vessel location map as to how it looks. As you can see, here's vessel location around Saudi Arabia. This is the number of US ships that are around Saudi Arabia. So obviously, you can see that the oil is safe. This is real, actual, live data coming in. So if anyone tells you the United States doesn't have a naval presence around Saudi Arabia, you're mistaken. This is the real deal. This is just incredible, actually. So you do see some interesting Deepwater Horizon oil slick. They were able to, you could actually, when you go to the data center, you can, like James Bond style, you could zoom this whole thing in, and high-level officials want to do that. They don't want some information on PowerPoint. They want to see just live zooming in, what's going on, what's the latest information coming out of there. It's all real time. So this is something that anybody could do, any government could do. Or it's not that you can't achieve the results in the regular way of doing so. I mean, this is ultimately programming, right? But the benefits of the REST-based approach are that overall, it's easier to do once you get your documents right. The overall infrastructure is much easier to manage. They're doing this just running 8-core blade servers, and they found that the amount of hardware they have not had to actually change their hardware for 3 years. So the resource utilization is really not that much. So there's a lot of interesting points here, right? It's just the speed with which you can get things done. The speed benefit comes because of the benefits of REST, that the state is just within the messages that are going across the components. I know it sounds really overly simplistic, but it actually isn't. Once you just get the hang of the tools, it really is as easy as I'm making it out to be. So this is the point. So this is it's just an overall diagram showing about all of the things that they've done: business services, core services. There's a team of about 14 people by Piro Systems, which is now part of Dell Services, that's managing this whole. By the way, they actually did a big POC, and they had chosen TIBCO and Fiorano, and they did a 1-year parallel run. 1 full year parallel run with both the products before choosing the REST-based approach, because basically TIBCO doesn't have the REST-based approach, and neither does IBM or anyone else. So, keys to success. Define what SOA means for your enterprise, really. For the Coast Guard, it meant widely distributed, limited connection assets, cannot be network-centric. Human intervention happens once in a way. But the key is the next 3 steps. build a little, validate a little. You can't just have architects who are only theorizing. It's very critical. Use narrowly focused, rapid turnaround pilot projects, right? And of course, you need organizational support. Final comment. This is from the Coast Guard. Bad architecture is usually the results of architects who don't program anymore, or who don't incrementally validate along the way. You don't have to program it, you have to validate. That's a bit of a direct statement. If you don't build it, how are you going to know it's right? This is very critical. These simple things have to be followed. It's amazing. So it requires you have to apply your theories to real problems, see if they work. The good thing about the REST-based approach is that at least the way we've done it is, it's ultimately just about components and messages. And the infrastructure supports that. So you're taken away from all this other central management of wacko documents and learning 50 different standards, or like BPL has this swim lanes. I mean, I don't need to learn swim lanes, I'm here to solve a problem. So there we are. So that takes care of my talk.
Okay, great.
7:45. What we can do is maybe take a small break now. There's just some coffee and stuff. And Jason will continue on this one.